In this video, we're going to look at some pericyclic reactions beyond the Diels-Alder reaction. The Diels-Alder reaction, of course, is the one we've already studied, and the whole essence of the Diels-Alder is shown in this molecular orbital interaction diagram. On the left-hand side here, I have the orbitals of butadiene, and on the right-hand side, the orbitals of ethylene. And a key thing, of course, here is that the homolumal interactions occur between orbitals of similar symmetry. So butadiene with 4 electrons has the filled orbital here of symmetric, and the second orbital is antisymmetric. Ethylene, the 1 filled orbital is symmetric. The key thing here is that the highest occupied orbital of ethylene, which is symmetric, matches the lowest unoccupied molecular orbital of butadiene, which is also symmetric, and even more importantly, the highest electrons here are in an antisymmetric butadiene orbital, and this HOMO matches the LUMO of ethylene. So this is indeed a completely allowed reaction. So is this symmetry allowed reaction? Yes, indeed. So let's just look at some other pi systems and see how it all works out in terms of orbital symmetry. So here is the allyl cation. Now the allyl cation would be three orbitals, but containing only 2 electrons. And so the allyl system, of course, is lowest orbital has no nodes, then there's 1 node down the middle, and then the top one is 2 nodes. But we only have 2 electrons, so it's a symmetric orbital. Now what's it going to do with ethylene? Well, ethylene, its filled orbital is still, of course, just 2 electrons. So let's look at the HOMO-LUMO match. Well, the highest filled orbital here is ethylene. It's symmetric. Is that going to match the LUMO of allyl? Antisymmetric. Oops. Symmetric filled orbital of allyl cation is going to match the empty orbital of ethylene. A, S, oops, sorry. What's the answer? A big fat no. Okay, so that doesn't work. So allyl cation, ethylene, that's a no-go. Let's change the system. Allyl cation and butadiene. Now we're talking. Look at this. Here now we have our symmetric orbital. What's the LUMO of butadiene? It's now symmetric. And the highest occupied orbital of butadiene, antisymmetric, matches the empty orbital of the allyl cation. So look at this. This one is, yes, it's allowed. So this one works. Allyl cation and a butadiene. Well, how would you do this reaction? Well, you need a source of allyl cation. Well, here's a one reaction. There are others as well. I'm going to show you one in the homework problem. This is a dibromoacetone. We're going to react it with zinc. Now this is kind of like forming a Grignard reagent in the sense of, but in this particular case, if we form an anion here, it's actually, of course, a enolate. So you react this with zinc. It's an oxidative addition reaction, and you form this complex here. Now, if you heat this up, this will spontaneously lose a bromide, and you'll form this cation. So that's a little strange-looking species, but just think of it as it's a delocalized cation. Now, if you take that cation and you allow it to react to butadiene, what are you going to get? Well, we just line it up. We said it was symmetry allowed, so the reaction should go. So what you have to do is just draw some arrows. So what's going to happen is the electrons, it's going to give up the zinc, reform the carbonyl. This pair of electrons will come down, attack this carbon. This will move over. This will move up. Here's our cyclic system of 6 electrons. That's what's the classic thing of a pericyclic reaction. Can you see what the product's going to be? Stop the video and see if you can draw it out. Okay, what is it? Well, it's a 7-membered ring with a carbonyl on top. So this is an example of a 4 plus 3 or 4 carbons plus 3 carbons, or usually the way it's said, we count the pi electrons. It's 4 pi electrons plus 2 pi. So 4 pi from the butadiene, 2 pi from the allyl cation. Very good. What else can we do? Well, let's go back to that allyl anion. It didn't work. It didn't work with I'm sorry, I'm mixed up. The allyl cation worked with butadiene, but how about the allyl anion? Well, let's look at this. Here our filled orbital is antisymmetric. Here the empty orbital is symmetric. So the allocation worked, but of course this is not going to work. A does not match S, and this then A does not match S. So allyl antibutadiene, you're out of luck. It ain't going to work. Is the symmetry allowed? No. So what can we do? Well, how about changing it a little bit? How about doing something completely different? We need a new pair that match. Here's butadiene, and over here I have hexatriene. Hexatriene. Now look at these patterns. They're all the same: symmetric, antisymmetric, symmetric, antisymmetric, symmetric, antisymmetric. And essentially, the way this thing works, it's almost like the Huckel rule. If the number of pi electrons, when you add them together, follows the Huckel rule. If you get 6 electrons, or in this case 10, you're going to find out that these patterns work. And it's kind of for the same reason, but because basically you need an odd set of filled orbitals on one side and an even set of filled orbitals on the other side to make the symmetries match. Because essentially what you have to do is you have to alternate one. So if you had an even number of filled orbitals on both sides, it'll never do a symmetry match. But here we have three sets of filled orbitals, and in 2, and 3 plus 2 is 5. That's a odd number, or corresponding to the 5 sets of orbitals corresponds to 10 electrons. That's how you can kind of figure this one out. So this is a 4 plus 6. Now, how in the world could we ever do a 4 plus 6? Well, we can. Okay, and here's one. And so this is a 4 plus 6. Now, this is a 7-membered ring. It has a carbonyl in it, but that pair of electrons from the carbonyl are involved in the bonding here. So we really have only 6 electrons in this system here. And here's our 4 electrons. And so this will actually work. We'll do a thermal reaction to draw out like that. Okay, so we actually now have, since we're dealing with 10 electrons, we have to have 5 arrows. Double bond, move over, double bond, form a new sigma bond, double bond, move over, double bond, move over, double bond, form a new sigma bond. So this is kind of hard to draw out, but you just I draw it out long bonds like that in Oscar, and then redraw it. It's a very weird looking molecule that looks like that, but this thing actually works. And if you redraw it in a more realistic way, it looks like this. That doesn't look so bad. And you can see the cyclopentadiene is this piece here, which just came down on the 7-membered ring. So that's pretty wild. Okay, well, what if your orbitals don't add to 6 or 10 electrons? Here's 2 ethylenes coming together. So can we dimerize ethylene? This is, of course, the case where the HOMO and the LUMO are the same thing. This is symmetric. That's symmetric. These are both antisymmetric. So no way. This is totally forbidden. It is not going to work. You can't do a 2 plus 2, and it simply ain't going to happen. And you can take two double bonds, and they are not going to dimerize. But shine light on them. This is the trick. This is the way you get the ones which don't meet the symmetry rule to work. You shine light on it. Now, you need UV light, because the energy difference between pi and pi star and ethylene is great enough that's out of the visible. You need UV light. But if you shine UV light on this, look what happens. The highest occupied molecular orbital now is antisymmetric. Look at that. It's antisymmetric. So it matches the LUMO over here. We now have a symmetry match. And this is pretty neat. Now, in this case, it's not as good as the regular ones, because we don't really have a symmetry match the other direction. But we do have this possibility where the free radical can form a new interaction with the other molecule. And it turns out this will work. In the excited state, we have, this is now quite a high-lying electron, so it really wants to spread itself out. And indeed, it'll do the reaction. And so here's an example. This is a double bond, and here is another double bond, and this one has an electron acceptor on it. And when you shine light on these, okay, here's our double bond plus the cyclohexenone. Shine light on it, you get a product. Now, this is an unsymmetrical situation. Are the two methyls going to be on the bottom, or are they going to be on the top? Well, the way you figure this out, because it's not just obvious, you look again at the coefficients on the orbitals up here, and you say, where is that free radical actually going to be located? So actually what we have to look at these anti-bonding orbitals. The anti-bonding orbital on the double bond is almost symmetrical, but it's a little bit bigger on the middle carbon here than it is on the top carbon. You see this green circle is a little bit bigger than the blue circle. That's because part of the blue is out here on the methyl groups from hyperconjugation. But if you look at the cyclohexenone over here, there's a huge difference. There's definitely bigger coefficient on this bottom carbon. So the rule is you want to maximize overlap, which means the two large coefficients are going to line up. So it's going to be this way, and you're going to have the A is going to be the correct answer, because that gives you the best overlap of the orbital. So A is what you're going to get. So the way you would draw this in terms of arrows, you would say the light essentially is going to promote the two electrons, and then the two electrons will join up with a free radical as free radicals from the two electrons from the double bond, and you'll form two new sigma bonds. And that's what we call the 2+2 reaction. It's a 2+2 photochemical reaction. So the 2+2 reaction, we would say thermally, if you just heat them up, the reaction is forbidden. But if you do it photochemically, the reaction is allowed. And it turns out that's the general scheme of all these reactions, is that if you have a reaction which is allowed thermally, that's fine. But if it's forbidden thermally, generally it's allowed photochemically, and vice versa. If you have one that's allowed photochemically, it's generally forbidden thermally. So that's the story, and a little confusing, but we don't have to worry about it too much, because luckily the Diels-Alder is so important. These other ones are a little bit more laboratory curiosities. You're not going to see them so much. Probably the second most important one is actually this one we're just looking at right now, the free radical dimerization of alkenes. That actually is used quite a bit, even though it's a bit more exotic. So have fun with this. There's a couple interesting problems down below.